Hi class, this is Mr. Morris, and we're going to be talking today about intramolecular forces and potential energy diagrams. This set of notes is specifically talking about covalent bonds, so keep that in mind as we're going through this. Also, if you didn't already watch the video on endothermic and exothermic changes, you might want to do that. That's going to be important in understanding these notes and the next notes. All right, let's start out just kind of by describing what a potential energy diagram is. Potential energy diagrams for covalent bonds, we have to think about Coulomb's law. Remember, according to Coulomb's law, energy is equal to K, which is just a constant, multiplied by Q1 times Q2 divided by R. Remember, Q just refers to the charge, positive or negative, of the particle. So if we have two charges, if they're oppositely charged, they're attracted to each other. If they have the like charge, if they have a like charge, then they are repelled by each other. Okay, so the attractive energy will be negative while the repulsive energies will be positive. Okay, attractive energy, that's if it's a positive and a negative, multiply those together, you're going to get a negative sign for your energy. But if it's a negative and negative, or a positive multiplied by a positive, in either case you get a positive energy, which represents a repulsive energy, since like charges repel. We could say the same thing about force. Still, it's a relationship between the charge and the other charge, and we're dividing by the radius. So the greater the distance between them, the weaker the force, the weaker the energy. So the attractive force will be negative, while repulsive force will be positive. All right, keep in mind that repulsive potential energy is caused by the interaction between the electron cloud of atom 1 and electron cloud of atom 2 and the nucleus of atom 1 and the nucleus of atom 2. That's just because like charges repel. So to break that down again, if we have two atoms and they are a certain distance from each other, they have some amount of repulsive potential energy involved because they have electrons in both of the atoms. They have electrons, and since they have a like charge, electrons always repel each other. They also have nuclei, and the nucleus of this atom and the nucleus of that atom are both positive. So they repel each other as well, like charges repel. We also have attractive potential energy in a system where we've got two atoms. So if we've got two atoms, the attractive potential energy is caused by the interaction between the nucleus of atom 1 and the electron cloud of atom 2. Opposite charges attract. Or we could say the nucleus of this other atom, atom 2, is attracted to the electron cloud of atom 1. Again, opposites attract, and then like charges repel. This graph kind of shows the different types of potential energy, attractive and repulsive. And then when we combine them together, we get something called the net potential energy. Here's what I want you to know about these graphs before we get started. The y-axis is the potential energy. If it is positive or above zero, it's repulsive potential energy. If it's negative or below zero, that's attractive potential energy. The y-axis, labeled by R, is the distance between atoms. And then, as this says, net potential energy is just your repulsive energy plus your attractive potential energy. It's when you're combining the repulsive and potential energies. For a bond to form, the net potential energy overall has to be negative. So let's look at what we've got going on over here. I've got repulsive potential energy up here. This little green line is the representative of repulsive potential energy. And the green line on the right side down here is representing the attractive potential energy, which is why it's negative. For a bond to form, when we add those together, we're going to get we're going to get their net potential energy. That's when we add up all of those values, we get the net potential energy. And for a bond to form, that net potential energy has to be negative. R sub 0, or you could say R naught, so we're looking at this point right here on the x-axis, that radius, that distance, represents the distance with most net attractive potential energy with energy of E naught. So it's the most attractive potential energy. In other words, the lowest overall potential energy, the most negative potential energy. Since this is the lowest potential energy, it's the distance with the most net attractive force, the most net attractive potential energy. The net force, which is going to be like the pulling or the pushing of the atoms to try to get either closer together or farther apart. At that point, at the point of lowest potential energy, the net force is also equal to the repulsive force and the attractive force, whether it's trying to get closer or farther apart. And at R0, that force is 0. The net force is equal to 0. Because the atoms are neither accelerating towards each other or accelerating away from each other. They're not trying to get closer together. They're also not trying to get farther apart. So R0 is known as the bond length. That's the distance between two nuclei in their most stable form. And E naught, or E sub 0, on the y-axis, that is the energy that's needed to break a bond if we're talking about a endothermic change, or the energy released when the bond is formed if we're talking about the exothermic change. It's the bond energy is what we would call it. All right, we're going to be evaluating the forces in this graph, and before we do, I want to look at a part of the simulation that you were supposed to do last class. All right, so this is a simulation of interactions between atoms. And as they're far apart, you see that the electrons are just kind of buzzing around wherever they please, from one side to the other side, and there's really not much change. As we move these atoms closer to each other, you can see that the electrons are spending a little bit more time between the atoms than they were. And they get closer and closer. You can see a lot of changes happening, and there's an attraction between the atoms now. And really what it is this nucleus is attracted to both of the electrons, this nucleus is attracted to both of the electrons, and that is what holds the bond together. So if I try to pull one away, the other one's going to follow. Or if I try to push them closer together, then they start to repel because the nucleus of this one is repelling the nucleus of that one. All right, I'm going to pause it here and move on to another part of the simulation. All right, this part of the simulation actually is very similar to what we're doing in the notes today with potential energy diagrams. So we've got these two atoms again, and we're going to have a graph generated that shows the radius on the x-axis, the distance between the atoms, and the potential energy is the y-axis. So it's the same thing that we've been looking at, but we can get a good visual on it. As I move these atoms closer together, the attractive potential energy, it becomes more negative. So we have the potential energy starts to drop down into the negative region more and more as they get closer together. Remember, that means that there's attraction occurring. They're close enough that they can have a strong attraction one to another. And you see the electrons being pulled toward the middle again. And right here they have a strong attractive force. But if I were to push them together, now we have repulsive forces because I'm trying to push them closer together than they want to be. So that spot where they are, the repulsive energy and the attractive energy are canceled out, and we just end up having no net force trying to pull them together or push them apart. is the minimum potential energy. It's the most negative or most attractive potential energy. So there's no net force of attraction or repulsion. That's why this is the ideal length between two atoms. We call that the bond length. And we'll get back into our slideshow now. Don't forget to work all the way through this simulation. If you haven't already done that, you'll find it helpful, I think. And remember, it is part of your homework assignment. All right, I'll go through this slide a little bit more quickly because we kind of talked about it in what we just looked at. Okay, we've got over here on the right side of our graph, we've got a greater distance between the atoms than any of the other spots on here. So the number 1 represents when the atoms are pretty far apart, just like what we looked at on the simulation. Atoms are too far apart for any significant attraction, so the net force is about equal to 0, and the potential energy is about equal to 0. Okay, and the second one, so number 2, represents when two atoms are getting closer to each other. As distance decreases, that radius decreases, the attraction between the atoms increases for a while until they get close enough. The potential energy becomes more negative, and the attractive force is greater than the repulsive force. So in this region of the graph, the attractive force is stronger than the repulsive force. Then we get to point 3, right here at the middle, where we've got our lowest potential energy. The distance for maximum attraction is what that is. The potential energy is the most negative, but the net force equals 0 because the attractive force, the force trying to pull it closer together, pull the atoms closer together to this point, and the repulsive force, the forces, if we were to try to push them too close together, that are pushing them apart to try to reach that ideal distance, the attractive force and the repulsive force have to be equal to each other, so we have a net force of 0. So the key points here, your attractive and repulsive forces are balanced in that point. The key point here is the net energy is negative, but the net force is 0. Just looking at your graph, the energy is negative, but the net force, or the attraction together, the pulling to try to get the atoms closer together, or the pushing to try to get them further apart, is actually 0. It's not trying to change the position of the atoms at all. It's that ideal length. So as the distance decreases even more, so if we try to push them even closer together, the attraction between the atoms decreases, the potential energy becomes less negative and eventually actually positive, and the repulsive force is greater than the attractive force, which is why those atoms will tend to be pushed back apart until they're back at this bond length again. The bond energy is the energy needed to break the bond. It's how tightly the atoms are held together. That's going to be represented by this, by the y-axis. When a bond is broken, it is endothermic. And the sign is positive. Energy is needed to break the bond. And when a bond is formed, that's exothermic. The sign of that is negative. Energy is released. You might need to refer back to the endothermic and exothermic notes if you're a little bit shaky on that. All right, we're going to pause here. The next video will go through some example problems.